step, how do they relate to each other? Welcome to join Charly Petty and me, Claire Shu, for this special Sports and STEM talk with SEM scholars. Question to everyone: do sports and STEM complement each other? So the answer is yes, they both activate our brains. Now, let's break this down more clearly. First, we have the amygdala, and its function is emotion and motivation. In sports, this is the drive to win, like the competitive energy. And in STEM, it's the same motivation that pushes someone to solve a challenging problem. Next is the motor cortex. This region controls motor planning and physical movement. So in sports, that's pretty obvious. It can be like sailing, swinging, running. But even in STEM, we rely on coordinated movements like writing equations, building prototypes, or working in a lab. Then we have the hippocampus and prefrontal cortex, which handles memory, like episodic, semantic, and working memory. Athletes use memory to recall plays and strategies, and in STEM, memory helps us store formulas, concepts, and retrieve information when solving problems. The prefrontal cortex is also especially important. It controls attention, focus, resisting distractions, and complex reasoning. Athletes use this to make split-second decisions under pressure, and STEM students use it for logical reasoning and multi-step problem solving. Finally, the default mode network and prefrontal cortex are involved in novel idea generation. So in sports, that might look like creative play or a new strategy. And in STEM, it can be like innovation where we think of a new solution or approach. So overall, both sports and STEM require motivation, focus, memory, planning, creativity. They might look different on the surface, but neurologically, they activate many of the same or similar systems.
There's also another effect called Flynn effect. So Flynn effect was discovered by the political scientist James R. Flynn, and this is run into the 20th century. So this is after analyzing decades of standardized testing data, and it was found that each decade the average IQ score increases by about 3 points. So essentially, say like every generation gets smarter. But he argued that this isn't because of innate effects, but rather because of environmental factors. So these can be through better nutrition, improved education, smaller families, or more abstract thinking in modern life, and also public health improvements. That is until I saw news occur on social media as well as some other news outlets about our generation, Generation Z, becoming the first generation to possibly become less intelligent, and it's maybe through AI usage as well as short form content. And so the neuroscientist Eric Newman, he found that the educational environment is increasingly centered on screens, and that could impact cognitive development.
The trend may be shifting, but we're not in this alone. Let's decide to get the odds together. Now let's talk about reasoning and tennis play. What if you follow a simple greedy algorithm? The simple greedy algorithm starts with a comfortable cross-court rally, which is the lowest immediate risk from neutral. Then the simple greedy algorithm will allow us to keep choosing the locally safest, lowest risk ball, which is cross-court, and eventually end up in a rallying state. Then the only way to finish it is with a high-risk winner-like shot. So for example, we go for a sharper angle or take the ball early and flatten it. And in this case, we change directions from cross-court to down the line. So the cumulative risk to win the shot is high. It's 1 plus 1 plus 6, which is 8 as our total risk. As you can see, the simple greedy algorithm is risky. Then, what would be a better way to win? Let's think about Dijkstra's algorithm.
So actually Dijkstra, it was I believe a mathematician as well as a computer scientist, and he was just shopping downstairs when his fiance, so he sat down and decided to find the shortest walking path, and among that he created Dijkstra's algorithm.
Dijkstra uses edge relaxation to repeatedly check whether a shorter path to a neighboring node can be found, and updates it if one exists. So now let's go through an example using Dijkstra's algorithm to find the shortest path from start to end. At step 1, we'll set the distance to start as 0 and everything else as infinity. So going to the smallest visited node, which is start, we can now relax the edges from start to A, and we can see that distance becomes 2. And we'll do the same thing, relaxing the edge from start to B, and we can see that distance becomes 5. Now we can mark start as visited. Then we'll proceed to step 2, where the smallest visited node is A. So we can relax the edges from A to C, and we see that A to C is 2 plus 2 equals 4. And since 4 is less than infinity, we can update C to be 4. Then we can relax the edges A to B, which is 2 plus 4 equals 6. But since B is already 5, and that's less than 6, we don't need to update B. And now we can mark A as visited. At step 3, we'll go to the smallest invisited node again, and this time it's C. And we'll relax the edges C to E, which is 4 plus 2 equals 6. And 6 is less than infinity, so we can update E to be 6. And then we can relax the edges C to D, which is 4 plus 6 is 10, and then update D to 10. And now we can mark C as visited. And at step 4, we go to the smallest invisited node, which is B, and relax the edges from B to D, which is 5 plus 2 is 7, and since that's less than 10, we can update D to be 7. And then we now mark B as visited. At step 5, we go to the smallest invisited node, E, and we relax edges E to F, which is 6 plus 5 equals 11, and then update F to 11. And then we do the same thing again from relaxing edges E to end. We see that E to end is 6 plus 15, which is 21. And then we can update the end to 21, and now mark E as visited. And at step 6, we'll go to the smallest invisited node again, which is now D, and we can relax the edges from D to F, which is 7 plus 2 equals 9, and that's better than 11, so we update F to be 9, and now we can mark D as visited. At step 7, we'll go to smallest invisited node, which is F, relax edges F to end, which is 9 plus 2 equals 11, and 11 is better than 21, so now we update the end to 11, and we can mark F as visited. At step 8, we see that smallest invisited node, which is end, is 11, and since there's no outgoing edges, we can mark end as visited. And now tracing back, we can find that the shortest path, or the shortest distance to end, is 11. Now let's talk about Dijkstra's algorithm in the context of tennis. So Dijkstra's approach is to optimize the total cumulative risk. It slightly increases early risk by pulling the opponent out wide. This creates imbalance and reduces the risk of finishing the shot later. So Dijkstra's path can become, for example, a neutral forehand cross court, then followed by a short cross court, which is slightly riskier, and now the opponent is stretched out wide and off the court. And this can be followed by a short ball and then an easy put away. So as you can see, the total risk is smaller. It's 1 plus 3 plus 2, which is 6, and that is less than the total risk of 8 in a simple greedy algorithm.
Hi, my name is Charlie and I'm from San Francisco, California. Today, we're at Jensen Beach at the U.S. Sailing Center for the Midwinter C420 Regatta. So far, it's been really fun and we're on day 3 of racing. There's 158 boats. Let me show you mine.
Hi, my name's Charlie and this is one of the boats I sail. It's called a 420 and we are currently at a nationals regatta for it. What I'm holding is the jib, which is one of our 2 sails. We use a system of pulleys to help hoist it up, to pull it up, so that way we can use it. We have the shackle. We clip it on this. Then I hoist it up with my line. It has a little thing up there that it runs through. Woo! Sorry. It's a little windy. These are the shrouds. There's one on each side of the boat, and then there's one on the front, but that one's called the forestay. I don't know why. Our mast hooks into this tiny little like shackle on the bottom. It like a little bowl. It sits in the bowl, but that's not enough to hold it up. So we have these metal wires, and then they connect to the sputters, which are those other metal beams, and then all of that creates like a triangle perfecto tension rig, so it can hold our mast up. If one of these broke, the mast would fall and probably get really messed up.
How do you decide how much tension to put on that?
It's mostly depending on the weather. The more windy it is, you want to pin down because it'll pull it more forward and it will like change the shape of your sail. And when it's lighter, you want to pin up. So right now we are at 5, but yesterday we were at 3 because it was much lighter. One thing you always have to have is the baler. We do have an auto baler in this boat. It's this like little latch that opens. If you see it right there, it's that black box on their boat. See that black box?
Yeah, I see it.
If you open that up, it makes like a tiny little ramp, and then that allows you. Sometimes it's a little too slow, especially when you're taking on a lot. So we have an Arizona iced tea jug with the bottom slashed off. We use that to scoop up all of the water, and then we dump it outside of the boat. The less weight in your boat, the farther you are away from being level with the water, so like you're more higher up, and then you go faster. You want as least water as possible. So get a baler. This is my trapeze. When it's really heavy wind like this, the boat wants to tip over and like flip in the water, and that is awfully slow if you're sinking. So instead, we have this little nifty thing. I usually have a harness on with like a metal hook like this, and then I take that hook and I hook it into this thing, and then I like lean out on it, and my feet are on the edge. And then since my body weight is all the way out on the boat, it's like a lever, and then we don't flip. This is our rudder, and it helps steer the boat. This bit right here, we fold it down into the water, and then as we push it through, it slices through, and then it helps angle our boat. Because if we were to go off with just sails, we could technically point, but it's much more difficult. We also have the centerboard, which helps guide the rudder into doing its job. It's an intern. Even though I said that there's technically 2 sails, there is a third. It's called the spinnaker, or a flying trash bag, because it's just this giant sheet of like plastic fabric, and it's kind of like a triangle, and then we attach one all the way to the top, then we attach the 2 edges to the outside of the boat, and then I'm like holding one edge and then the other edge, and I'm keeping it full. And since we are downwind, I'm not hoisting that right now. It'll fly away.
But it's in here, right?
Yeah, it's in here. Ours is American flag colors. It's red, white, and blue.
And so what do you pull to make the spinnaker come out?
To pull it out?
Yeah, like if you were gonna go downwind.
I would pull this up. And this would lift up. This is the port side, so it's the left, and then this is the right side. This is the head, it's labeled. And then it like fills. And then I have a pole to help me on the side that I'm not like actively trying to trim in. And then I take that pole and I attach the middle onto this hook.
Yeah.
And then I attach it onto one of the. Oh, I finished up. Oopsies.
Beep.
And so then I attach it to one of these ends. Like I would clip it right here, and then as I push that out, it will offer me more stability. And we call that end the guy. And then I run it back to here. These are my spin sheets, and then I would adjust it like this to keep it full and happy.
So in sailing, these are not called lines, these are called sheets?
No. It's like when people call it rope. Rope is called line, and then when you're using it for a sail, it's called a sheet. And then when you're using it to pull something up, like to hoist it, it's called a halyard.
Cool. Walk me to the back of the boat. How do you steer?
This is the mainsail. It is currently attached to the boom because there's a little. Here, let me try to rotate it. You see this hole? Our sails have this like tiny little edge that's thicker, and so we thread it through this, and it gets like stuck in there. So then it creates the shape for our sail, and then we attach it down there using the out haul. So it pulls it out. Then we take the front of the boom, this hole right here, and we attach it to this pin. It doesn't look like it'll stay. There's other styles that like lock it in place, but this one, it's going off a truss. And then over here is this, there's another one of these like weird hole things. And we take our main and we thread it through this, and we bring it all the way up top. And then that's how you set up your mainsail. Next, we put it through this system down here. It helps us pull on as much as possible, and how much we want to pull on depends on how much wind there is. So we want a lot more if there's a bunch of heavy wind. Oops. And we want a lot less if it's lighter wind, because the more we pull on, the more it moves our mast forward, and the more our mast is forward, the more control we have. It also changes the shape of the jib by making it flatter.
hope you enjoyed these STEM insights. Please consider joining us at SV Young Scholars. Thank you.